Hello, and welcome to a general overview of how data is handled in IOGRAM. In this video, I will go over how the graph solves, the different levels of data access for the graph nodes, data trees and their operations, as well as a number of other useful components related to manipulating nodes and their data. So at the heart of IOGRAM is the graph, and visually this is represented by the graph view here, which is on the right hand side of the screen. And at its most basic level, the graph consists of nodes and connections between those nodes. So in this case, I have a sphere node or component and a mesh renderer component. And then I have a connection between the mesh output of the sphere and the mesh input of the renderer. And the idea is that graph components are responsible for doing things such as creating geometry or retrieving information about that geometry or maybe reading a file. And the links allow the data that's created in those nodes to be passed between other nodes and to create complex and interesting behavior really quickly. So our implementation of the graph has a couple more features which are really important to at least kind of introduce. First of all, and this is not uncommon in other sort of flow graph implementations, nodes might have more than one input and output. And this is very important because most interesting functions are going to need a variety of input. Having multiple outputs is very handy because apart from sort of the main body of the function, the main return value of the function, there might be a bunch of other related information that needs to be presented as well. In our implementation, output nodes are allowed to have more than one connection, but input nodes can only have a unique connection. So here, if I try and connect this up, you'll see that the existing connection is deleted and replaced with the new one. This might change in the future, but for now, this is how it works. You can also right-click both the input slots and the output slots to either edit their value. So in this case, I'm setting this value to 1, or inspect the output. So here I can see that the new sum is in fact 1. Our implementation of the graph also has two modes of solving the graph, and these two modes are the quick solve and the full solve. And to illustrate the difference, I'm just going to grab an input component that allows me to move objects in the scene. So it takes a node ID, and now when I click and move my mouse in this node, I actually move the position of that sphere. So what's happening here is that the sphere and the mesh renderer nodes in the quick solve of the graph are not being updated. So the sphere is not being recreated and this mesh renderer is not being rerun because the inputs have not changed. However, the object move component is being constantly updated. So in a quick solve, nodes whose inputs have not changed are not resolved. And this is very important for generating behavior to the graph, behavior with the graph that is not all done in a single shot. However, there is also the full solve mode, which is triggered in certain circumstances, which will recreate the graph entirely. So I'll just do that again. I'm quick solving here to move the sphere around, but a full solve will reposition it back at the origin. And that's because the sphere node and the mesh renderer node are being rerun. The third important feature of our implementation of the graph is how we pass data between the nodes. For this, we use a tree-like data structure that allows the nodes to interact in a very rich way. So to illustrate this, I'm going to build up a grid of points. Now there's actually a grid component in IOGRAM, but to illustrate the role of the tree data structure, I'm going to use more basic operations. So consider this series of numbers that I've created based on a certain step size. If I hook this up to my construct vector component and display it, I get a series of points along the x-axis. But what I'd really like to do is create a grid of points in the xz plane. And so if I try to hook up the same series to the z coordinate of this vector component, I simply get a series of vectors in a 45-degree angle. What I'd really like to do is for every element in this series, I'd like to create a set of 10 vectors. And so to do this, I need to transform the output of this series component into a more appropriate data structure. So I'm not going to go into the details of how exactly this works or some of the more advanced features of data trees. However, I will point out that the graphed component found under the tree category of components does exactly this. It takes a series of elements that in this case are all on a single branch, and it puts every element onto its own branch. And when we hook that up now to the construct vector component, we get exactly what we want. And if we examine the output, you can see that we have a series of 10 branches with 10 vectors on each branch, creating a grid, a 10 by 10 grid. And of course we can then adjust the step size, and we can see that we get exactly the sort of behavior that we want. To see a slightly more involved example using data trees, consider the problem of creating a series of hexagons that we want to actually loft into some sort of pillar-like structure. So to get started, we use the hex grid component to create our base of hexagons. And so attaching a slider to the x, y, and z dimensions of this grid, we can get sort of a bunch of hexagons. But what we'd really like to do is take this, this plane of hexagons and transform it by some vector in the y direction. And so that the hexagon grid component actually has an input for the transform, which you can use to create the grid of hexagons. So I've gone ahead and created a very similar setup to what we just saw, a series of numbers that create a series of vectors. These are used to initialize the positions of a transform. And then I've also used those same vectors to initialize the rotations of that transform. So now if we hook this up to the hexagon grid, we actually get a sort of tower of these things. And if I adjust the step size, I can get a smaller or taller tower. And if I adjust the rotation, I can get a little bit of rotation in these hexagons. Okay, so currently I've rendered these hexagons using the curve renderer, but I'd actually like to create some geometry with this. Specifically, I'd like to loft every vertical arrangement of hexagons into a sort of pillar. But here's the problem. Our tree structure that comes as a result of the hexagon grid is not well suited for this. And it's not well suited because it actually groups together every hexagon in each plane on a single branch. So for instance, these bottom 7 hexagons are on the first branch, and then the next set of hexagons are on the second branch, and so on. And in order to use the polyline loft component, we actually have to give it all the hexagons that are vertically arranged. So this whole column here, and then this whole column here. So this is another very common tree operation that happens. And for this, we use the flip matrix component. And so what the flip matrix component does is it takes a tree with, in this case, 10 branches and 7 elements on each branch, and it creates a new tree with 7 branches and 10 elements on every branch. And this is exactly what we need in order to group the vertical columns of hexagons into a single branch. And now when I use the polyline loft component and I render it using the mesh renderer, I get exactly what I need. And here we can play with the settings a little bit, and because the tree-like structure maintains the arrangement of that data, we can adjust the parameters without adjusting the setup of the tree structure. And this means that you can explore sort of families of solutions in a really interesting way. So most of the components that deal with how data flows through the graph are contained in the sets category of the component library. And to close off this tutorial, I'm just going to go over a few really useful ones in this category. So one of the first things that tends to happen when building up logic with a graph is you end up with a lot of components on screen. And this is not necessarily bad from a purely logical point of view, but it's visually fairly confusing. So in IOGRAM, we allow multiple views to be exposed of the same graph. And so the way you do this is simply by creating another instance of the graph editor. So for every view in the editor, if you click in the top right-hand corner, you expose some controls for that view. So in this case, we're going to split the graph view vertically, and we're going to create a new view called mesh loft. So these are 2 views into the same graph structure. And what that means is that although you don't see the nodes in this new mesh loft view, they are logically there. However, since the way you interact with the nodes is based on the editor UI, we need some mechanism to interact between the 2 views. So for this, we have the 2 components, export view data and import view data. And so the goal with these is that every view should have a kind of single or maybe 1 or 2 purposes to it. And then it exports the results of that view through the export view data component. So in this case, we have created some hexagons and we have transformed them and twisted them. And then the second part of the view really has to do with lofting them and doing mesh operations. So this is a very logical place to make a new view. So what I'd like to do is, after I've flipped the matrix of curves, I'm actually going to export that result. And I'm going to call it hexes. And what the export view data does is it creates a global variable called hexes, which I can import elsewhere in the graph. So I'm going to delete these 2 components, and I'm going to go down to the mesh loft view. I'm going to use the import view data to grab the hexes global variable, and if I inspect the output here, you can see that it has in fact picked up the results of that, or the contents of that global variable. And then if I use the loft operation exactly like we did before, and render it using a mesh renderer, using a keyboard shortcut Alt-M, you can see that we get exactly the same thing back. So this mechanism of splitting more complex bits of logic into multiple views is essential for maintaining clarity in the structure of the graph. So that's it for our overview of how data is handled. There is a lot more to say on this topic, but I think we'll leave it there for now.